Hundreds of meters of vertical drop separate the construction zone from the ravine floor in the Andes Mountains of South America. Engineers here split sheer cliffs to pave a massive road through conditions where a single error carries catastrophic weight. Why force infrastructure onto such near vertical slopes? It seems safer to bypass these geological giants entirely. But without this risk, vast regions remain isolated for centuries, cut off from the rest of the continent. But this is just the beginning of the challenge. It seems impossible for machines weighing hundreds of tons to operate here, but in reality, they cling to the slopes with calculated traction. One can notice how drill rigs bore into the rock for precisely controlled blasting. Every detonation utilizes millimeter-level calculations to keep the foundation stable. Dust slowly settles over the steep mountainsides as the equipment gradually carves a winding path that traces the topography like a steel thread. And this is not the limit. The construction moves forward, turning stone barriers into a unified network. 4,500 meters is the maximum elevation reached by highway construction crews working in the Andes. In the high-altitude regions of Peru, Chile, and Bolivia, building roads is a direct confrontation with some of the harshest terrain on the planet. The thin air at these heights creates a physical barrier, reducing labor efficiency by 30 to 40%. One can notice how the weather conditions shift unpredictably from intense sunlight to heavy snowfall within just a few hours. But the difficulties do not end with the climate. Why is more than 6% of the total project cost diverted away from the road surface itself? At first glance, the budget allocation seems skewed, but in reality, this funding is strictly required for massive rock excavation, slope stabilization, and landslide prevention. Without these measures, any pavement laid would be destroyed by the mountain. Engineers usually tackle these mountain roads in two distinct stages. The first stage follows the outer cliff face, where heavy machinery cuts the route directly into the stone. One can notice how crews install anchors and retaining structures to stabilize the slope and protect the roadway from rockfalls. The process is only gaining momentum. When the terrain becomes too steep or visually unstable, the strategy changes. Construction shifts to the second stage, tunneling deep through the mountain. This approach allows the road to bypass the most dangerous sections entirely. Thus, the infrastructure avoids exposure to landslides and extreme weather, ensuring a stable passage for future traffic. Hundreds of drill holes mark the future trajectory of the route on the sheer rock face, precisely defining the construction boundaries. Why is the center line determined with such extreme precision before a single charge is laid? It would seem sufficient to simply blast the interfering rock mass to clear the way for construction, but without strict adherence to the pre-calculated plan, the explosion could compromise the overall stability of the mountain, burying the entire project under rubble. Engineers carefully load explosives in controlled amounts to break the rock in sections, ensuring the surrounding cliff remains intact after each blast. Excavators immediately move in to pick up and remove the fragmented soil and stone from the construction surface, scooping up debris with hydraulic power. One can notice how heavy-duty trucks position themselves along the very edge of the abyss to receive the load from the excavators. They operate continuously along temporary access roads, hauling debris to designated disposal areas planned in advance. In certain sections where the terrain allows, bulldozers push the material directly down into the river or steep slopes below to shorten the time required for site clearance. Bulldozers take on the role of shaping the road by pushing away excess material and carving the mountainside into the initial roadbed form. At first glance, this process looks like a chaotic movement of earth, but in reality, the blade is constantly adjusted to achieve the required slope and elevation. This creates a rough but stable surface for further operations. But this is just the beginning of the transformation. The cycle of drilling, blasting, excavating, bulldozing, and grading repeats section by section until a continuous roadway takes shape, firmly anchored to the dangerous cliff face. Trucks deliver graded aggregate or crushed stone, dumping it in long strips along the road alignment to build the foundation. It is visible how wheel loaders move in to scoop and redistribute the material evenly, preparing it for the next construction layer. Motor graders run along the route, spreading the material into uniform windrows and adjusting the elevation precisely according to the longitudinal and cross-sectional design profiles. Because dry material will not bond correctly, water trucks spray the entire surface to control dust and create suitable moisture conditions for compaction. Vibratory rollers or steel wheel rollers then begin compacting each layer, moving in multiple overlapping passes to achieve the specified density. It gets more complex further on. In curved sections or areas close to the cliff face, graders continue to fine-tune the road edges and cross-slope to ensure proper drainage. Compaction continues as rollers move along the route again in multiple overlapping passes to create a firm, stable, and uniform roadbed before the surface layer is constructed. Therefore, in narrow sections or areas where rollers cannot access, workers use hand-operated compactors to finish the task. One can notice the machine densifying each layer of material to prevent localized settlement of the roadbed. This ensures uniform compaction even in the most inaccessible zones of the route. Workers secure themselves with safety harnesses and carefully climb the steep cliff face to access the rock surface directly, suspended above the void. They use pneumatic drills to bore into uneven sections, breaking off protruding rock blocks to flatten and stabilize a slope. This work is carried out point by point with continuous checks on the surrounding rock cohesion to prevent sudden rockfalls or slope failure. And this is not the limit of the safety measures. All workers wear full personal protective equipment, including helmets, safety harnesses, masks, and gloves to minimize risks while working in extremely hazardous terrain. The entire cliff face is eventually covered with a protective steel mesh, which helps secure loose rock fragments and reduces the risk of rockfalls onto the roadway below. Workers spray a thin coat of liquid asphalt onto the roadbed to create proper bonding between the structural layers. This asphalt coat is then heated using gas burners, allowing the solvent to evaporate and activating the asphalt's bonding properties. One can notice the heat and smoke rising from the pavement, indicating that the asphalt remains at a very high temperature during the laying stage. The paver moves slowly along the road, continuously receiving hot asphalt mix from dump trucks feeding directly into the front hopper. Behind the machine, the heated screed keeps the asphalt in a workable state while spreading it into a smooth, continuous surface. Workers stand on both sides of the paver, closely monitoring the edges and using shovels and hand rakes to correct uneven areas or sections close to the road shoulder. But machines cannot reach every inch, so some workers follow directly behind the paver to treat joints, gaps, or curved sections where the machine cannot maintain full control. Since interruptions cause defects in the layer, the pace of both the paver and the supply trucks must remain steady. As the machine advances, a continuous strip of black, freshly laid asphalt gradually takes shape. The process concludes this phase, opening the road to the final cleaning stage. Workers use high-pressure sprayers to clean the surface and remove any remaining loose stones or excess material. It is visible how the spray nozzles are moved evenly to ensure the roadway is clear and that the asphalt's bonding and surface quality are not affected. Once the asphalt section is completed, the road surface gradually cools and becomes a solid, continuous layer, clearly revealing the curves that closely follow the mountainside. From above, the winding road resembles a black ribbon draped across the cliff face, marking the completion of an engineering work built in extremely harsh terrain. 90 degrees is often the angle of the cliff face where traditional road widening becomes physically impossible. Why do engineers stop cutting deeper into the mountain at this specific point? It would seem logical to just blast more rock to create a shelf for the highway. However, the geology dictates a vertical approach because there is simply no longer enough stable ground to support a standard foundation. Instead of excavating, the road must be suspended along the mountainside using a complex system of reinforced concrete columns and modular sections. These massive pillars are built directly onto the solid bedrock below, acting as the primary structural skeleton that will eventually hold the entire weight of the traffic above. But this is just the beginning of the structural transformation. Most construction materials cannot reach these heights by conventional means due to the lack of access roads. Therefore, heavy-duty cranes and specialized aerial transport equipment take over the logistics. One can notice how giant components are lowered from above into their exact design positions with slow, calculated movements. The equipment gradually maneuvers heavy loads against the backdrop of the precipice, ensuring that every element lands on its designated mark. It gets more complex further on. Once the columns achieve their required strength, the installation of road deck modules begins. At first glance, this process resembles assembling giant building blocks, but in reality, it is a high-stakes operation where a single inch of misalignment compromises the integrity of the route. Each module comes prefabricated to standard dimensions, containing pre-installed steel girders and concrete slabs. This method significantly reduces the time spent on hazardous on-site construction. It is visible how the connection points slot together as the heavy slabs settle onto the columns. Workers operating at dizzying heights remain constantly secured by safety harnesses. One can observe the close coordination with crane operators required to precisely align each component before it is locked down. The structure gradually forms a continuous roadway that hugs the natural contours of the mountain face. Drainage systems and safety barriers are installed immediately after the surface is finished to ensure long-term durability. And this is not the limit of the engineering design. This adaptive approach allows infrastructure to exist sustainably in the harshest environments without destroying the landscape. By reducing the need for massive rock excavation, the project balances modern structural engineering with the raw constraints of nature. The road deck is now ready to receive its final paving layers without haste. 200 meters is the vertical distance the ventilation shafts must rise to reach fresh air. When neither carving a road into a cliff face nor building on supporting columns is feasible, engineers route the path directly through the mountain by constructing a tunnel system. But the project takes its first deep breath long before the main tunnel is dug. Why is the ventilation system the very first priority? It would seem logical to start excavating the main passage immediately with heavy machinery. But without an artificial network, heat and pressure at these depths would make the air toxic in minutes, rendering human labor impossible. Engineers drill vertical shafts 4 to 6 meters wide using the raise boring technique. The drill head pushes upward from inside the mountain with near-perfect precision to create the exhaust route. Sensors constantly monitor oxygen levels and coordinate powerful jet fans to keep the airflow steady. One can notice how the system acts as the lungs of the project, expelling toxic gases. But this is just the beginning. Outside, the construction site is shrouded in a thick haze of dust. 15 meters is the diameter of the cutter head, the heaviest component weighing over 1,500 tons. Specialized transport vehicles deliver the system in modules, carrying parts ranging from the control cabin to the hydraulic units. Auxiliary tunnels are widened and reinforced with sprayed concrete and steel to accommodate these massive segments. At first glance, assembling such a giant seems like a crude industrial task, but in reality, it demands the precision of a laboratory operation. In the confined space illuminated by hundreds of industrial lamps, laser sensors align modules with a tolerance of no more than 5 millimeters. Powerful hydraulic jacks lift the cutter head into position step by step. It gets more complex further on. One can see the fully assembled tunnel boring machine stretching nearly 100 meters in length. It equals the size of a 30-story building laid on its side. Thousands of mechanical parts fit together to form a unified steel giant, ready to pierce the solid heart of the mountain. Electrical and pneumatic systems come alive from the central control cabin. Because the machine weighs over 3,000 tons, it advances slowly, yet with unstoppable power. The rear section is still being assembled in the launch chamber, while the head is already buried deep in the rock. Precise coordination ensures that water, air, and power conveyors run without interruption. The process is only gaining momentum. 4 massive hydraulic cylinders press the cutter head against the rock with up to 500 tons of force. 23 alloy discs spin with immense torque, crushing geological layers as hard as steel. One can notice how high-pressure water jets constantly cool the metal to reduce friction. Each drilling cycle advances exactly 1.2 meters and takes roughly 30 minutes. The machine repeats this process more than 50 times per shift, day and night. Once a cycle ends, the gripper shield pushes forward and hydraulic clamps lock onto the tunnel walls. The crushed rock travels out on automated conveyors to clear the path. And this is not the limit. Machines operate 24 hours a day on monumental projects like the 57-kilometer Gotthard Base Tunnel or the Santa Lucia Tunnel. China currently leads this frontier with over 1,000 units simultaneously carving railways and subways. But the stopping of the drill does not signal the end of the work. Engineers enter the tunnel carrying measuring instruments instead of heavy drills. Pressure sensors and ground-penetrating radar scan the walls to detect cracks thinner than a human hair. High-frequency ultrasound and 8K optical cameras inspect every bolt to ensure flawless safety. Everything only gets more complicated. because safety is paramount, systems are tested under strict international standards like NFPA 502. Control rooms track smoke sensors, jet fans, and the 10-megawatt backup power system in real time. Therefore, the tunnel is declared ready only after reading and vibration analysis reaches perfection. The infrastructure is finally prepared for daily use beneath the Earth's surface. 3 major phases mark the completion of this high-altitude roadway. The process moves from dangerous excavation while clinging to the rock face to the precise erection of concrete pillars. At first glance, the finished road appears simple, but in reality, it requires traversing the very heart of the mountain. The structure now stands firm against the elements. One can notice how the highway weaves through the stone. Why was tunneling chosen for the final section? The external slopes proved too fragile for construction. Excavating the interior ensures stability, finally opening the route for traffic.